I am Tangashakti from EEE Department, Rohini College of Engineering and Technology. In this lecture, we are going to discuss about spectral density. So here, the spectral density of the signal describes the power present in the signal as a function of frequency. That means the power present in the signal per unit frequency. So the power spectral density is commonly expressed in watts per hertz. The unit will be watts per hertz. Next one, energy spectral density. So for the derivation of energy spectral density, we have to consider F of T being electric potential in volt. So that will be applied across a resistance of 1 ohm. So the total energy dissipated in a resistance is given by E equal to integral minus infinity to infinite f square of t by r into dt. So here the value of r will be 1. So here the function f of t is generally a complex number. So here the Fourier transform of f of t is the f of j omega. So by Parseval's theorem, we can get integral minus infinity to infinite f square of t into dt equal to 1 by 2 pi integral minus infinity to infinite f of j omega the whole square into d omega. Next here the energy in the resistance can be written as so the resistance value will be 1. So we can write E equal to integral minus infinite to infinite f square of t into dt equal to 1 by 2 pi integral minus infinite to infinite modulus of f of j omega the whole square into d omega. So here the function modulus of f of j omega the whole square is the energy spectral density. So simply we can say the energy density. So it will be represented by a special symbol of epsilon ff of omega. That is epsilon ff of omega. That will be approximately equal to modulus of f of j omega the whole square. So here this is the continuation of the previous derivation. So its integral is equal to 2 pi times the spectral density. So E equal to 1 by 2 pi integral minus infinite to infinite E epsilon f of omega into d omega. So here for the spectral density for the two signals f1 of t and f2 of t. So here the energy will be integral minus infinite to infinite f1 of t f2 of t into dt. So here also we are considering the resistance value will be 1 ohm. So by Parseval's theorem we can write integral minus infinite to infinite f1 of t f2 of t dt equal to 1 by 2 pi integral minus infinite to infinite f1 of minus j omega f2 of j omega into d omega. So here the f1 of t and f2 of t are the real values, means we can get f1 of minus j omega equal to f1 of j omega, f2 of minus j omega equal to f2 of j omega. So here the normalized cross energy is given by capital E f1 f2 equal to integral minus infinite to infinite f1 of t f2 of t dt equal to 1 by 2 pi integral minus infinite to infinite f1 of minus j omega f2 of j omega into d omega. So this is the normalized cross energy of the two signals. So we can write epsilon ff of omega equal to f1 minus j omega f2 into j omega. So here it is the cross energy spectral density E equal to 1 by 2 pi integral minus infinite to infinite epsilon of f1 f2 of omega into d omega. So instead of f1 of minus j omega into f2 of j omega, we are substituting eff of epsilon ff of j omega. So next we are going to see the power spectral density. So for the power spectral density is denoted by Sx of f. So this that will be get by the definition of the Fourier transform of the autocorrelation function. So this is the expression of the power spectral density. Thank you.